Okay, now the quizzes and the exams and all those discussion is over. Let us get back to the lecture. This was the problem that we left you with last time. Hopefully you have solved it, or you have attempted to solve it. You see, I keep on telling you that the best way to study is to hide the solution and to attempt the problem yourself. If it's a simple problem, okay. If it is a tough problem, try it 1 time, 2 times. Don't give up. Don't give up until you feel that you have really solved it, and then compare with the solution. Right? So, okay. So now, hopefully you have already solved it. That is why I keep on telling you that please finish the current lecture before you come to the next lecture. Before you come to the next lecture, finish the current one, revise it. If there is any problem, solve it. Okay, so it is a design using fracture mechanics approach. It is a pressurized spherical pressure vessel, right? Pressure vessel. So it is spherical in nature. There is a uniform internal pressure of P. The internal radius is R. The wall thickness is T. And at any point, there is a central crack of 2A. There is a central crack of 2A. Now, if it is a spherical pressure vessel, you know that there is a radial stress in this direction, and the tangential stress is the hoop stress, right? So that you know. So this is the problem, that initial inside pressure P, radius R, thickness T, not edge crack, internal crack, central crack of 2A. And now what is the issue? First design approach is known as yield before fail. Yield before fail. When will it fail? It will fail as a result of the formation of a crack of critical size. There is a crack right now of some size 2A, suppose it is 1 millimeter. It will grow, it will grow, it will grow until it becomes, say, 10 millimeters. If the 10 millimeter is the critical crack size, then after that there will be rapid propagation of the crack and it will be suddenly failing. So you find out what is the critical crack, then you know that it can keep on deforming. It will not fail until it reaches the critical crack size. The plastic deformation of the wall may be observed, and the pressure within the tank can be released before the occurrence of the catastrophic failure, because now it is yielding, it is changing in shape. So you can close the pressure, you can remove the pressure vessel, whatever. So based on this, materials having large critical crack lengths are desired. Crack length, right? This is the critical crack length, not the current. There is some current crack length, but any material which will crack at a bigger length is good, and any material which will crack at a shorter length, critical crack. Therefore, you go to table B5, look at the different materials and find the critical size, critical crack size for each one of them. And then anyone which has a large critical crack size is good. Suppose the initial crack is 1 milli. In one material, after it reaches 2 millimeters, it fails. In another material, after it reaches 4 millimeter, it fails. In other material, until it reaches 10 millimeter, it does not fail. You see, so initially it is 1. But which material allows the maximum life? Where it can go to 10 millimeter before it will fail. So that will be your best material, right? So this is your approach. And therefore, there is only this equation. There is no other equation. There is one equation, remember, the Griffith crack equation. But in the Griffith crack equation, we have the material property called specific surface energy. Here in the table that we showed you last time, we have the K1C values, fracture toughness values. So based on fracture toughness values, there is only this equation. There is only this equation. The equation is K1 is equal to Y sigma root pi A. Remember, K1 is equal to Y sigma root pi A. Now K1 will become K1C when the sigma is the critical sigma and the A is the critical crack size, isn't it? So now your question is here, of course, this critical crack size you have to find out. Critical crack size you have to find out. So this is the unknown. So the only decision is that what will be the critical stress? What will be the critical stress? What was your condition? Yield before failure, yield. So it means automatically that the yield stress is the highest value of stress that you will allow, right? Because you have to put in the equation some value, what value should be used for the critical stress of the material when it will have K1C. So here, because you are saying that yielding is allowed, so therefore maximum stress is yield stress. But you know that in design you have some factor of safety, So here in this book they are using capital N as the factor of safety. So yield strength is the maximum stress allowed, but divided by some factor of safety. That is your design stress. To always give some safety factor. So if this is 2, then half of yield strength is your maximum allowable, right? So this is it. This is the whole theory of the problem, that you use the equation K1 is equal to y sigma root pi A, where K1 will become K1C if sigma is sigma critical and A is A critical. For sigma critical, because it is yielding, so sigma y divided by the factor of safety. Once this equation is there, we have to find this value. Therefore, square the equation, take AC on the other side, and you have this, right? N square y square pi K1C square sigma y square. Why are we writing like this? 2 reasons. One is that K1C and sigma y both have the same units, megapascal. This is megapascal root meter, this is megapascal, so you don't have to change any values, don't have to write 10 raised to 6, this will be directly there. But what is the other reason? Otherwise, I could have written N square K1 square upon y squared pi sigma y square. But we have separated this, right? Why? Tell me. We are comparing different materials, right? When we go to table B5, we will take material 1 and find AC, then material 2 find AC, and so on, and then rank them. Factor of safety, will this change? No, factor of safety is your design factor. So whichever material you choose, you are giving the same design factor, so N is the same. What is Y? It is the geometry factor of the crack. So whatever the material, the geometry factor is geometry factor, it is not affected by the choice of material. And pi is pi. So even if you remove these, you cancel these out, then your comparison is still the same. I write the actual value of N, the actual value of geometry factor, the actual value of pi. But this will be the same every time, isn't it? Because this is not related to the material that I select. So I can remove this and this and this, and I only compare K1C by sigma y whole square. This now is a property of the material, and this is a property of the material. So as soon as you change the material, then this changes. Yes. So therefore now this is your whole approach. That if you wanted to apply the yield before fail criterion, then it means that your material can expand, deform, but it will really fail only when the current crack becomes equal to the critical crack size. Therefore, you put yield strength as the critical strength, of course divided by safety factor, and then find the critical crack. What is the size of the critical crack in each material? Okay, so this is it. So now these are the materials, right? This is the table B5. Different materials: steel alloy 1040, 4140, 4340, aluminum alloys, right? Other types of alloys. So stainless steel, aluminum alloy, magnesium alloys, titanium alloys. These two values are the fracture toughness, K1C. This is in SI unit, this is in pound square inch unit, and this is the yield strength. So of course, because the yield strength is given only in megapascal in this table, it is not given in KSI, therefore we use these values and these values. So that is it. For each material, K1C divided by sigma y whole square. So the table is continuing: graphite, ceramic, semiconducting materials, silicon nitride, polymers. You see, so the table is a very good, nice, large table of lots of engineering materials, which means metals, alloys, ceramics, polymers, and so on. Okay, so this is the table. Of course, if you can compare any one or two of the materials, then all the other values you will do in a similar way. So, right, remember from the K1C equation, you separated out AC on one side, and finally because the other three quantities will be the same for each of the materials, therefore you are just comparing the K1C upon sigma y, a square of that. Okay. So if you have already done that, if this was your approach, then this is your answer. If you see, we are showing some of those materials, medium carbon 1040, magnesium alloy, aluminum alloy 2024, titanium alloy 4140 steel, 4340 steel, and so on. And of course 4340 steel tempered at 425, tempered at 260, different temperings. And each time from the previous table, you are taking K1C upon sigma y in the megapascal units and just comparing this square. So this value will represent the crack size. So from 1 millimeter, for example, if you can go to 43 millimeters, there is a large amount of deformation before it can fail. But if you have to go to only 20 millimeter before it can fail, if you have to go to only 5 millimeter before it can fail, right? So this is your best material, this is second best, third best, and so on. So this is it, right? Of course, repeatedly doing the calculation for 10, 20, 30 materials is not the idea here. If you can do that for 3, 4 materials, but the thing is that unless you do it for all the materials in the table, you don't know which value was the highest value. The theoretical application, your understanding of the problem is finished even if you do it for 2 materials. That you see, the whole approach is that I take my critical stress as sigma y divided by factor of safety, because it is yield before fail. And then using this criterion, I compare the AC, the critical crack size for each one of them, and that is it. So the approach is okay even for 1 material, 2 material, but unless you apply it to all, say, the 20 materials in the table, then you don't know which one will give the maximum value. But that is it, right? So if it is in a quiz or exam or something like that, maybe I can give you only 4, 5 materials, and then you can apply it to all of the 4 and 5 materials and you are done. Okay, good. So now to the second part of this design problem, the second part. An alternate design approach, you know, it is called leak before break. So rather than reading here, you already understand it, but let me remind you, leak before break means what? There is some current existing crack. Normally this crack can spread throughout the pressure vessel, and then in the end the whole pressure vessel cracks into 2 pieces, fractures and so on. But rather than spreading throughout the body of the pressure vessel, if this crack goes through the thickness, in the thickness direction, if it starts to grow in the thickness direction, then after some time, whatever thickness it has, 2 millimeter, 3 millimeter, 10 millimeter, if it goes through the thickness, then there will be a hole in the wall. And as soon as through thickness crack is there, the hole in the wall is there, then whatever extra pressure is there will be released, right? It is now a leak. So now the whole pressure vessel will not crack, will not burst, will not fracture. Only once the crack goes through the thickness, then it is a through thickness crack, and that means that now it can start to leak. So this is this other approach, right? The first approach is yield before failure, and the second approach is leak before failure, right? And using this approach you solve. So we will continue with this.